Ladies and gentlemen, hello and welcome, coming to you once again, not quite live from One Take Studios, where I am recording back-to-back episodes today. So today I am talking about estimating mu when sigma is unknown. Alright, I am doing this as an add-on to a previous video, which was estimating mu when sigma is known. So I'm going to be making some references here to my previous video, so if I say something that seems unfounded, please go back and watch the previous video. But today's probably a little bit more realistic. Alright, because we are again trying to estimate mu, so we have a population out there, we don't know what its mean is, we're going to try to find an estimate for it. But this time we're also saying that we don't know sigma, which is kind of logical. If I don't know the mean, I also probably don't know the standard deviation. And so this is the more likely circumstance of the two videos, the previous one and this one. Alright, so we're going to make some changes to what we did in the last video, and hopefully you can do some comparing and to see what happened here. Alright, so first off, and this is going to hopefully make sense, not only are we using x bar as a point estimate for mu, which would make sense, sample versus population, x bar is going to stand in place of mu for now, but we are also using s to approximate sigma. Again, totally logical. If I don't know the population standard deviation, I can use the sample standard deviation to approximate, to get an approximation for that, and to hopefully then run some calculations. Alright, what else does this mean? Well, okay, here's the thing, is that we will no longer be using a normal distribution. In order to make S the stand-in for sigma, we are using a student's t-distribution, also sometimes known I think as Gosset's distribution. Alright, and so the student's t-distribution has a lot of similarity to normal. Alright, so that it's going to see, it actually looks kind of similar actually in everything. I think one of the main differences is that there's thicker tails in the student's t-distribution than there is the normal. But the shape of it ultimately depends on n. So our sample size controls the shape of the student's t-distribution. Which means, oops, hold on, one more thing first. Degrees of freedom, someday when I'm not self-taught, because everything I'm teaching you today is all stuff that I figured out on my own, there's something called degrees of freedom that's associated with student's t-distribution. All it is the sample size minus 1. So if I had 30 in my sample size, this would be 29. I don't know why it's a thing. Apparently it's a thing. But part of that is to help look up numbers on tables, which sounds oh so exciting and slightly archaic. Yes, there we go. Alright, but this should make some sense. Alright, as the degrees of freedom increases, which means that your sample size is increasing, this is going to approach normal. And so this is why this is going to be an acceptable usage here, because while it is not normal, if we get the larger sample size, it becomes normal. Okay. Other things that then are kind of parallel to previous universes that we've seen, we have calculated z-scores before. Well, if we don't have a normal distribution, we don't have z-scores. So if we have a student's t-distribution, I guess that makes these our t-scores right here. Which the process is similar. We have seen for z-scores that we do x bar minus mu, trying to find out how far apart the actual value is from its counterpart. Same thing, but we're dividing by s over the square root of n. So not just the standard deviation, but the estimate for the standard deviation divided by the square root of our sample size. So very similar to things that we've seen for z, except it's t this time. And other things that are similar would include, last time we talked about z sub c being a critical value. Alright, so that makes this time t sub c is going to be our critical value. Again, this is how many, can I say? I can't say. I'm gonna close my mouth right now. T sub c is the critical value taking the place. So in other words, we're talking about along our axis for our distribution here. These are going to be counting how far we are away from the center. Okay. Alright, so we've got all that stuff. Other things that we should know that are strikingly similar. Here we go, folks, here we go. We talked last time about having a maximal margin of error, and this plays a key part in developing our confidence interval to get our good estimate going for mu. Well, again, you'll notice some similarities to last time. The last time we did this, we had E for error. We still have that, capital E. But instead of Z sub C, our critical value we just got done saying is T sub C. So we've got this value instead. Again, this is not going to be the confidence percentage, but it's going to be the score that's associated with it. And again, typically this is something that we would look up on a table for students' t-distribution. But notice then here we are doing S divided by the square root of n instead of sigma because we don't have sigma, so using S makes sense. So if we can find this margin of error, we can get the ball rolling on our interval, which is calculated then essentially the same way because our confidence level is the probability that mu is someplace between the estimate for mu and then plus the margin of error minus the margin of error. This is the exact same as last time. We just calculate the error slightly differently, but it works the same. So again, that means that this piece right here, this becomes our confidence interval. And that's, again, the probability that it's going to, ooh, not the probability, oof, rawr. I'm just going to keep shutting my mouth because I keep putting my foot in it. All right. Okay. So if I wanted to have a 99% confidence interval, this would then be adjusted to the fact that I've got under my almost not quite normal curve, 99% of my data, very small tails, kind of spread out. All right. I showed you last time an example that we did kind of by hand. This requires a gigantic table that looks things up. And again, the likelihood of you using this in your life is probably slim. If you're taking an AP test, again, go find a different video because this is not that video. What I want to do is actually go to our technology aspect of things. All right. And I'm going to show you a twist on last time. So I've got a candle company that I made up. It's kind of a small candle company, but these are their sales for the last 5 months. All right, so $2,462, $2,117, 2020 because it's just that kind of year, $2,396 and $2,684. So this is sales over the last 5 months. Based on what we are looking at here, we are saying that we do not know the mean amount of sales per month, and we also don't know the standard deviation for all the sales that have ever taken place for this company. I am going to say that we are assuming the population is approximately normal. Why is this important? We don't have a very big sample size, all right? And when we talk about this being dependent upon n, we still would really like to see a sample size of 30 or larger, or know that there's something that's close to normal. And since my sample size right now is 5, that is nowhere near 30, so since I don't have a very large sample size, I'm going to start with the assumption that it's approximately normal. So yeah, I made that example up. You'll have to trust me a little bit. Okay, and you know what? Since it's my made-up company, it's normal. There we go. I just declared it. Okay, so what can we do with this? We would need to know fun things like the critical value, T sub c, which we're not currently looking at the table. We could find S for this. We could find the standard deviation, and we know n. And we could find a mean for this, for our sample. We could find all that stuff. Let me show you something a little bit different from my last one. All right, so I'm going to switch screens here. We're going to check this out. And what I did is instead, I opened up a new document, and I opened up a spreadsheet, and I put my 5 months worth of sales into that spreadsheet. All right, so that's a good place to start. Check out what our options are here. Again, everything fun and exciting is in the menu, and we can work with statistics right now. We are still doing, oh, no, escape. We are still doing a confidence interval, but we're not talking z-scores this time. We've got t interval. Let's use t, all right, for our students' t distribution. That would make sense. All right, last time I said we were going to do, last time we did a z interval, I said we're going to use statistics, stats, instead of data. That's assuming that we have the stats, that we know X bar, that we know S. I'm going to keep this with data for this example, just so that you can see a comparison. And I'm going to say, okay, this is great. Notice it's not going to ask me for X bar or S. It's going to say, hey, where's your data? Where's your list of numbers? And since it's in column A, that works out really nicely. And I have a frequency of 1, which is good. You know what? I'm going to go with a slightly larger confidence level this time. I'm going to go with 99%. Again, think about what that means. In order to be 99% confident, I'm making the interval bigger to make sure that it's included, hopefully. And the results are going to be in column B. That's okay. All right. So, well, that was handy. Check it out, guys. So the confidence level, our lower boundary, is, and again, this was in dollars, so this is still going to be in dollars, this is going to be, I'm going to write it down, $1,782.93 on the low end. And on the high end is $2,888.67. So those are the limitations that I have for my interval. And I'm saying that I am 99% sure that mu is between those values. I'll come back and show you my written version of that in a moment here. But, again, lower, upper. Here's the x-bar. We didn't calculate it, but the calculator did. So we are saying that the $2,335.80, this is smack dab right in the middle of these two values, because everything in the interval hinges on this center point, the x-bar, taking the place of mean for the moment. And then from there, if we take this value and we add $552.87, that puts us here for the upper. And if we take our x-bar and we subtract $552.87, that gives us the lower. So again, this is the margin of error. The interval is centered at the mean, the sample mean, and we use the margin of error to go up and down from that number to create the interval. And, degrees of freedom is 4. Well, that makes sense because we had 5 numbers total, and 5 minus 1 is 4. And in case you wanted some more information, they also calculated S for us, so that was our standard deviation, and our sample size was 5. All right, so we have all this information, and it's a secondary way that you could potentially run this, either as data or statistics. And so this time we ran it as data because we had the data. All right, so jumping back one more time here, let's go over here. So we are saying that we believe that for the sales of candles, for the monthly sales specifically, that the mean is between these two values. And we are saying that we are 99% confident that mu is in this interval right here. 99% confident that mu is in this interval. All right. So again, by way of reminder, we are saying that when we do an estimate for mu, it is not a number, it is an interval. This is that interval. If we want to be more confident, the interval gets bigger. If we are less confident, that's because the interval is smaller. And I think I want to make just one more point here real quickly in saying this. Please understand that we are not saying there is a 99% chance that mu is in this interval. Chance is future. What will happen? Mu already exists. We don't know it, but it exists. And either it is in this interval or it is not in this interval. So we never want to say there's a 99% chance that mu is here. We are simply saying we are 99% confident that mu is in this interval. And that is a subtle difference, but it's an important one. Okay? All right, so again, if something here didn't make sense, you may want to go back to the previous video where we talked about what happened when mu was known. Mu was known, rar, when sigma was known. And otherwise, there's a ton of parallels here, guys. It should look really familiar. And enjoy, play with it, take really good notes though, all right? Because this is not going to stick well in your brain the first time through, and that's okay. All right, thank you.